Arthur Ashkin invented the optical tweezers. And he did this in 3 steps. He realized that he could, using the radiation pressure from a laser, push a small micro-sized transparent sphere in the direction of the laser beam. He also realized, the middle panel, that because the laser beam is not homogeneous, it's more intense in the center, the sphere will be pushed into the center by so-called gradient forces. And finally, he took a lens and focused the beam so that he could keep the small sphere fixed in space. Of course, it wasn't the fact that he could trap a small sphere that was the real breakthrough. The real breakthrough came when Arthur Ashkin demonstrated that he could trap in the tweezer viruses, bacteria, and even living cells. Now we come to the second part of this year's Nobel Prize, to Gerard Moreau and Donna Strickland. And what you see here is the development of laser pulse intensity as a function of time from the very beginning, when the first laser was constructed in 1960 by Maiman, and up to 1985. And what you see, there is first a rather sharp increase in pulse intensity, but then it levels off. And this became a problem because the technology of that time was not scalable. It was not possible to go to higher intensity because of amplifier damage. And the way to come over this hurdle was the invention of the chirp pulse amplification by Moreau and Strickland. And this was really the core of Donna Strickland's PhD thesis. So the idea and what they demonstrated is the following. You take a short pulse, you stretch it in time, maybe a factor of 1,000. And then the amplitude of the pulse will decrease, also a factor of 1,000. Then you take the pulse and send it through the amplifier. The pulse is increased in amplitude. And finally, in the final step, you compress the pulse so that it has the same duration as your input pulse, but now with a much higher intensity. After the invention of the CPA technique, basically every 4 or 5 years, the pulse intensity doubled. And this gave a possibility for a rather wide range of applications, both in basic science and in more practical applications. High-intensity, ultra-short pulses. They are between 10 to 100 femtoseconds. 1 femtosecond is a million of a billionth of a second. And in the upper panel, you see very high-intensity pulses coming roughly 1 per second, like this. And these pulses can be used for laser particle acceleration. You want to accelerate electrons or protons. And this is now a development that we can already see could be of importance for cancer therapy in the future. In the middle panel, you see pulses coming roughly 1,000 per second. The intensity is a little bit lower, and these pulses are adopted to a new field of science called attosecond science. And attoseconds is even much shorter than a femtosecond, 1,000th of a femtosecond. And by using these attosecond pulses, you can explore how electrons are moving in atoms and molecules. Very short time scale. In the lower panel, the frequency has increased even more. There are now 100,000 pulses per second, but the intensity is a little bit lower. And these pulses are extremely useful for high precision interaction with matter. And I give you one example how they can be used. This is now a CPA femtosecond laser that is used to correct myopia or nearsightedness. And the femtosecond laser is in the cornea creating a small lens-shaped piece of tissue, which is called a lenticule. The femtosecond laser is also used to make a small incision in the cornea so that the lenticule can be extracted with a small instrument. And by doing this, you are decreasing the refractive power of the eye so that your focus is now on the retina and not a little bit before the retina. And so finally, we are today awarding the Nobel Prize for groundbreaking inventions in the field of laser physics to Arthur Ashkin, Gerard Moreau, and Donna Strickland.